Okay guys, let me run you through a couple of little things on this intro for further implicit differentiation, the questions here on this topic. Let's take an example here. We've got a function here, but we've got a product. Basically, you look at it from the outside in. So from the outside, in terms of its structure, it's a product, it's u times v. The u is okay, that's a simple function of x which we can differentiate. But the v here is itself a composite function, isn't it? It's a function of a function. So it's e to the something. So we have to use the function of a function rule when we do that. So let's do this differentiation, and then we'll use the notation that's mentioned over here, y dashed instead of writing dy dx, and we'll use y double dashed instead of writing all this d2y by dx squared. So differentiating then, let's differentiate the product. It would be u. The v dx, e to the something differentiates to e to the something, multiplied by the something differentiated, and 2 lots of y differentiates to 2 lots of y dashed. So that's u dv dx plus v e to the 2y times du dx, and x differentiates to 1, is equal to, now this itself is a function of x, it's a function of a function though, isn't it? So let's use the function of a function rule. E to the something differentiates to e to the something, multiplied by the something differentiated. 2x just differentiates to 2, doesn't it? So that's what we've got there. So now what we can do, and more often than not we do this in these problems, is because we're asked to show that this equals a certain differential equation, what we can replace the e to the 2x by here, if we wished, is we can replace it by x e to the 2y here, or we can just simply differentiate again. So let's differentiate once more, and we'll get x u dv dx. Now this is a problem, isn't it? Because if we did that as u and that as v, then we can't benefit from the fact that we've already differentiated this up here. So in problems like this, what we generally do if we have to differentiate this again is we label that to be the u, because we already know that this u that is in the line above differentiates to this. So that will save us some work. So here, if we're differentiating, then we'd say u dv dx, and 2y dash differentiates to 2 lots of y double dashed, plus v, which is the 2y dashed, times du dx. And we know what that differentiates to because it's here and we've just done it here, so we can write it in. X e to the 2y times the 2y dashed plus e to the 2y. So we've replaced that, that's the v dx here, these two things put here, is equal to, and then we've got differentiating this, another 2 comes down, doesn't it, to make 4e to the 2x. And here, e to the 2x we can replace by x e to the y, so that would equal then 4x e to the 2y. And that would then lead to, what would it lead to? Let's see what it leads to here, shall we? We've got an e to the 2y common all the way through, every single term, so we can divide by that all the way through, and that's what a lot of problems ask us to do. So here we've just got 2xy double dashed, that's that term there. Then when we expand this bracket, we'll have 2y dashed times another 2y dashed times the x. So we'll have 4x y dashed squared. Agreed? And then this term here, e to the 2y times 2y dashed, will be plus 2y dashed e to the 2y plus 2y dashed e to the 2y, and then this 4x can be moved over, minus 4x to this side of the equation equals 0. The e to the 2y can go, of course. We're just left with 2y dashed, aren't we, because we divided by that. I forgot to omit that there, didn't I? So there we are. So oftentimes we're asked to show that this equation here, when you differentiate it, leads to this second order differential equation. And this is the sort of process that's typically involved. You generally have to be very careful when you differentiate, because there's functions of a function, and there's also functions of a function inside products as well. And you generally have to replace this at some stage at the end of the problem because this will still be there in the problem, and you can replace it by this and then get the equation that's asked for in the question. So all the best for this section then, guys, and I'll catch you in the next one. Cheers.